Okay, so I guess we'll start. Just share screen. Okay. Yeah, guys, I'll see the questions. So first question, I guess it's a little numerical, but I think it's useful. So if I have monochromatic light and it has a wavelength of 600 nanometers and it passes through like a fast shutter, like let's say a camera, then what will the spread of wavelengths be? So does anyone have an idea of how to approach this problem? Okay, so basically, okay, I can share solution. 1 sec, let me pull it up. Okay. So basically, it's an application of the Heisenberg uncertainty principle. The reason why I wanted to share this problem is because like light isn't like monochromatic. There's always like some like variation to it because of the Heisenberg uncertainty principle. So yeah, so if we use the Heisenberg uncertainty principle, we get the energy time form. We can get h delta omega delta t is less than or equal to h bar over 2, or greater than or equal to h bar over 2. And then, so we set it equal to h bar over 2 for the minimum. And then the shutter is just the delta t here. So that's like, I had Professor Williams. So this was, so you plug in the time here. So you get that, so you get that the delta omega is equal to, or the spread of frequencies is 1 over 2 times the shutter time. And then you just use the relation that omega is equal to 2 pi f, and then you get yeah, the frequency, which you can then convert to wavelength and get yeah, the wavelength here. Yeah, so that's just a review of the Heisenberg uncertainty principle. So now we move on to the next question. Notes, share, okay. So the next question I wanted to ask you guys is, when can you use the Maxwell-Boltzmann approximation? Well, first of all, what is the Maxwell-Boltzmann approximation? Okay, so you have the Fermi-Dirac approximation, which is like 1 over 1. I can't remember if it was plus or minus. I think it was like plus, and then exponential of like a bunch of stuff like, let's see, the Fermi energy over, what's it, KT. And then the Maxwell-Boltzmann approximation is just the same exact thing, except you delete the 1. So it's just this. So you get 1 over the exponential. And so you're able to use this when E minus EF is greater than KT. So when E minus EF is approximately greater than or equal to 3 KT. This is because that if this is greater than around like 3 KT or so, then this term like dominates the 1, if that makes sense, the exponential term. So like we know that e to the 3rd power is much larger than 1. That's the reasoning. Okay, and then are there any questions about that? Okay, I just thought this would be useful because if you ever have a question where you need to use, let's say, the Fermi-Dirac distribution, this is a lot harder to work with than the Maxwell-Boltzmann distribution. You most of the time you can just get away with using the Maxwell-Boltzmann distribution. Okay, so next question. If you increase temperature, what happens to the depletion region width? So I'll give you some time to think about that. Yes. So why does the width increase, Alexandra? Isaac?
It's proportional to temperature in the square root in the formula.
Yes, that's true. So we know that width is proportional to square root of the built-in voltage, and it's also proportional to natural log of 1 over an I squared, but VBI will dominate the natural log. So, and then VBI is, yeah, that's right. Okay, so why does junction capacitance occur?
Because there's a separation in charge at the junction.
Yeah, that's right. So that's precisely why junction capacitance occurs. And then what bias are photodetectors in solar cells in? And why is that? So they're actually in reverse bias. I guess a couple questions to consider is how are photons generated? And another question to think about. Okay, so how are photons generated? Another question to ask is, do solar cells create or consume power? So they're in reverse bias. Solar cells, they generate power. So you'd see them in quadrant 4. If you unlike the IV curve, photodetectors are also in reverse bias. So why is that? Um, yes. Photons, yeah, they're from the electron hole pairs. So they're in reverse bias because the reason you would have a photodetector is you only want current when there's light, right? So so we only want current when the light photons hit the phototransistor and create electron hole pairs. And so also these devices in reverse bias allow the width for the depletion region to increase, which allows the area to absorb more photons. And greater potential across the depletion region also allows for higher drift velocity of carriers. So I think it'd be useful to also see a diagram for, where did it go? It's not here. I had it here somewhere. Okay, there it is. There it is. Okay. So you can see the IV curve for the PN junctions here. So here we have a breakdown voltage. When it's in reverse bias, the voltage is so high that it causes the basically what happens is the N and P, the diodes, they like flip, right? So the P becomes the N and the N becomes the P, and yeah, it kind of breaks. And then for the reverse bias, this is when you have a photodetector. And then this region right here is quadrant 3. That's when you have a photovoltaic cell. And this is when you have a transistor. And the last conceptual question that I have for today is, so the transistors in your computer, why are they in forward bias normally? Okay. What a transistor is a it's basically a PN junction with I guess 3 ports. So I guess since you guys didn't cover transistors, I'll just explain this one. Basically, the reason so they're normally in forward bias. The reason being that for a computer, like it's not trying to like detect a certain event or anything. What it's trying to do is basically as soon as you get some type of like so basically in your computer you have the transistor and then you have some like power source, right? If the power source is off, then I mean there's not current there. If the power source is flipped on, then it's going to be in forward bias, and so it's going to like it, yeah. Then it wants like current to flow once you like have that switch, basically. Yeah. And then so finally, like study tips I have for EC2. This class is pretty equation heavy, so it's good to prepare a cheat sheet full of equations and know what they mean, how to use them. And yeah, try to understand what's going on in different like setups too, like reverse versus forward and stuff. And I guess Rafael can share his questions now.
Hi. Sorry, I'm a little like not too skilled with Zoom, but if I'm allowed to share my screen, can you make me one of the co-hosts, please?
I've made you
Nice.
host.
Oh, can you make my iPad though? So I can share my screen. There's two me's. I guess I can make myself the host, huh? So sorry, guys. Okay. Can you guys see my screen? Oh, I can see it. Okay, cool. It works. So I was thinking going with like a little bit more of problems, I guess. So the first problem is this was from a final for an EE2 course that my professor gave us just because he's mean in a later course. So the question is a certain state has a probability of 15% of being empty at 300 Kelvin. So it's what is the location with respect to the Fermi level. So we have that the probability that a state actually, do you guys know what's the probability of the state being occupied? Because if you know that, you could figure out the probability of it being empty, right? So the probability of a state being occupied is actually the Fermi level. As Cody was saying, it's a very important concept. So we have 1 minus the Fermi energy. That will give us the probability of a state being empty, because we know that this is the probability of a state being occupied. They tell us that that's a 15% chance. So goes to 0.15, and if you solve, then you have the probability is equal to 0.85. So now you can use the Fermi-Dirac equation because you know the probability. So that'll be 1 over 1 plus the exponent of E minus EF over KT. You know that this is equal to 0.85. So if you solve for E minus EF, which is the location with respect to the Fermi level, the energy level with respect to the Fermi, do you guys want me to go through that math, or can I just skip directly to what the answer would be? Like the equation, I would.
A question here, Rafael. Can you use the Boltzmann approximation here?
That is a good question, Cody, actually. Well, as you mentioned, as long as it's within the 3K, 3KT, the difference between the Fermis, you could approximate. I think we could solve for that. It's not being asked, but it's always good to know. Actually, there is a previous question on this, which is literally finding the error between the Maxwell Boltzmanns and the Fermi. And it's such a mess. I was actually gonna go over it, but it's a little long and complicated, and I think it doesn't really add much. It's more like a cool thing to know when to use it, but I figure since you guys have a final, it's most important to know when to use the equations. I guess since no one replied, I'll just go over the math of it. So you would have You're solving for E minus EF. So it will be 0.85 times 1 plus the exponent. And then this would be E minus EF is equal to KT the ln. So if you put this in a calculator, your result will be that E minus EF is equal to negative 0.045 eV. The reason why it's a negative is because the Fermi level is below the energy level. I mean, sorry, the energy level is below the Fermi level. That's what the minus sign means. So that's it. That's what you were asked for. You were asked the allocation with respect to the Fermi level. So I feel this is a good question because it doesn't really ask you. Oh, yeah, it's good to know KT as 0.026 EVs rather than having to memorize what the constants are. Anyway, so I think it's a cool problem because it gives you probability. Doesn't explicitly tells you that you have to use the Fermi-Dirac statistics to find the difference. But you know, it's good to know. I thought it was a cool problem. Another problem that I have for you guys. I'll create a new page. So it's asking for a p-n junction. Is the n side of it's 5 times the doping of the p side, and it gives us the. I can highlight that. The problem is long, but it's important to just know the important parts, which is it tells you the n side doping is 5 times the p side doping. It tells you the intrinsic carrier concentration is 10 to the 11. Band gap is 2 eV at 100. This is a cool problem because it gives you 100 Celsius, not Kelvin. So one thing the professor told us, a lot of people got it wrong because they didn't change Celsius to Kelvin. So always check those things. They tell you that the built-in junction potential is 0.65, and they ask to know what's doping of the p side. So how does anyone have any ideas? How will you approach a problem like this? I can tell you step 1 for me would be convert the 100 Celsius into 373 Kelvin. Okay. I guess another cool thing, I always like to take the problem and bring the statements of the problem as parts of like what I need to do. So the problem tells me this. Now I know that's one of the things that I know. Another thing is said to me is that ND is equal to 5 times NA. It's another big hint from the problem. Still, I don't know how to solve it, but what I do know is I have the built-in junction potential. Do you guys, I don't expect anyone to know it, but it should be in the formula sheet. But the formula for the built-in potential, it's KT the ln of Na and D over Ni squared. So now we're getting somewhere because they ask you to find what's the doping on the p side, and you're given built-in potential junction. You're giving a relationship between p side and n side of the doping, and you're giving a temperature. So maybe we can use the function for built-in potential and solve for Na. Right? That seems like a good approach. So again, I'll ask you guys again. C A over like Ca over 2 like junction capacitance?
Yeah, there's a formula. I mean, the original formula is C equals epsilon A over depletion width, but then you can simplify that to a longer formula.
Yeah. So I guess you could use the approach with the depletion width. Yeah, you could. Actually, you're asked if you notice for part 2, what is the depletion capacitance? So you do have to do that. That comes into place. I don't see why you couldn't use that to begin with, but as you said, it's a pretty long formula. So perhaps this is a faster approach. And I think in that case, you would need to know the junction capacity. You would have like an extra variable that maybe you don't have. So you couldn't really solve entirely for it. Like you would always end up having either Na or junction capacitance or depletion width. But it's certainly, yeah. I mean, if you go that route, you probably find out that you still need one more equation, and it will lead you back to this built-in potential. So since this is like a lot of algebra that I just think is not really, I hate when professors do that, but it is really something like it would take some time. And I think if you guys want me to go through it, I can go through it, but we're going to try to solve for Na. That's like our objective. I guess I'll do the highlights of it, just like it's not entirely a waste of time. So it'd be I kt. We can take the exponent of that. And if we replace this in here, we will get 5Na squared over Ni squared. Okay. And then from that, you can solve for Na squared. It's going to be Ni squared times the exponential of the built-in potential over Kt, right? Yeah. Over 5. And then if you solve for, at least for me, I like to do things to not throw everything at once in the calculator in case I made a mistake. So if you find the answer for this should be 1.19 10 times to the 30 centimeters cubed squared. And since you care for Na, then you just take the square root of that. And the result is 1.09 10 times to the 15 centimeters cubed. So that is the doping concentration. You know, the number does make sense. I feel it's a good thing. It's always like a sanity check, I guess. If you get something like 10 to the 6, that's like not too, preoccupying, because it should be somewhere around like 10 to the 11, 10 to the, because they give you the intrinsic being 10 to the 11. So if you have something below that, then you know your answer is not correct. It has to be more than the intrinsic. Because it's a dope PN junction. Part 2 of the problem asks you to find the depletion capacitance for a 2-volt reverse bias diode. So to do that, that is the long equation that you said. So we would use that C is equal to epsilon A over WD. Now you could put directly here the WD equation, but I like to do it in parts. I don't think, I feel it gets really messy if you just go directly into it. So what I'll do is I'll do WD is equal to 2 epsilon V total over Q times Na plus Nd over Na Nd, this whole thing square rooted. So for this, I will skip the math because it's really a lot of algebra. And I really feel this part is not going to add too much to you guys just to know how to do this math. But one thing that I do consider is important is we could use Na we know the relationship between Na and Nd, right? So you could directly use that in here and just do the addition and division. But I personally prefer, in cases like this, just stick to what you're giving in the problem. You know, you never know. Maybe you punch it has happened to me. I punch a number wrong in a calculator, and this number might not be accurate. Maybe my approach is right, but my number, the end number, is not right. So I always like to stick to what the problem gives me, because that one way or another has to be right. As long as you know the approach, you know, you should be getting the right answers. So without going into a lot of detail of like the simplifications, you can replace ND for 5 times NA. And if you combine all this, you're going to get the WD is roughly, oh, it's another one. It's roughly 1.8 micrometers. Are you guys okay with that? Like, I could really go over the simplification. I just don't really think it's worth it. But if you guys want to, we could go over it. At least the way I did it. Okay, great. Thank you. Okay, so now that you have the width, the depletion width, you can just go to the capacitance. And, you know, I believe they give us epsilon. So they tell you that the dielectric constant of the semiconductor is 10. So this would be epsilon naught times epsilon relative, which is 10, times the area over the depletion width. They also give you area. So if you solve for this, and this is like just plugging numbers at this point. You already have this, you're giving the area. This should give you something around 2.45 nanofarads. Again, nanofarads feels good. It's a good number. I always get preoccupied if I get like a really big number for capacitance, because it's usually around the nanofarads. Is everything clear in regards to this problem? Does anyone have like a specific question? Maybe want me to? I'm not gonna draw qualitatively the correctly sketch for the band diagram, because that really takes a lot of time, and it's really doesn't really add much to none of the problem. I feel is more important to being able to read a problem and identify which equations you gotta use based on the information that you're given. So does anyone have any questions? Okay. So the other problem that I want to do, it's they give you a graph and they ask you stuff about it. It's always fun, huh? Oh, it's not that graph. Oh, I think it's this one. Yeah. So oh my God. I was trying to do this before sharing my screen, but it proved to be a lot harder than what I anticipated. Okay, so they give you this, and they ask you to select the answer in terms of like what you're seeing, you know? So the first question is it in thermal equilibrium or is it out of equilibrium? For this one, I'm ask you guys to, you know, give it a shot. Just why, and I mean, what do you think it is and why? Wow, deep thoughts, guys. Okay, so it's okay. I guess I'll go with the first answer. So this would be out of. Whoa. Oh, okay. So my pencil die. Of course it did. I'm sorry. Guys, give me like 1 second.
I think while we're waiting for Rafael to sort out his stuff, so for the Fermi energy level, if we are not in thermal equilibrium, is it well defined or no? So if you're not in thermal equilibrium, the Fermi energy is not well defined. And so we define something called the quasi-Fermi energy level. It's like a fake Fermi energy level. Just like the effective mass is like a fake mass. It's not really a mass, but it's like, you know, it gets the idea across. It's like the same idea.
Oh my God.
I have
Hello, can you guys hear me?
a little echoey, but I think it's good. Sorry guys, having a little bit of technical troubles. Wait, Rafael, do you want me to go through a couple numerical examples while you get some stuff sorted out?
Okay, can you guys hear me?
Yep.
I'll take that as a yes, hopefully. Okay, this is okay. Whatever. I'll just share. So I'm not the host for some reason. Could you make me the host, Cody? Sorry. Okay, thank you. Okay. Okay, cool. So as Cody was saying, yeah, when you have some disturbances, I mean, sorry, not disturbances, but it's not in equilibrium, you have some quasi-Fermi levels. So it's not really Fermi levels, kind of like quasi. So this is out of equilibrium, right? And other than what Cody said, there is something else. It's a big giveaway as to why it's in out of equilibrium. The reason is there's a slope here. So if it was in equilibrium, it will be flat. But if you apply an electric field, it could go like that, it could go like that. And so you can see it's a little tilted. So that's a good way to tell that it's out of equilibrium. And okay. The energy has a slope. So is it uniformly doped or is it non-uniformly doped? Does anyone want to take a guess at it? Why is it like what it is and why? Okay. This one is actually non-uniformly doped. Oh, it's uniformly doped. How can you tell if it's uniformly doped? If it wasn't, the distance between the Fermi and the conduction band would vary as you move across the x-axis. So as you move this way, if it was non-uniformly doped, you would see a difference between this distance. But as you can see, across the whole picture that you see, the distance between the conduction band and the Fermi are constant. So you can safely say that it's a uniformly doped. The other question, is it a p-type or is it an n-type? I'll give you a hint. The more you dope something, the closer it gets to the conduction or valence band. So maybe one approach for this would be see which band it's closer to either the conduction or the valence band. Like, you know, so is this distance bigger or smaller than this distance? So obviously the one that's closer is the one that has more doping. So just because you're closer to the valence band, it's safe to say that that's a p-type. And I guess it's worth to mention where all these things are coming from in case, I don't know, maybe you guys are curious about it. If you recall these equations. This should be, this is quasi. Yeah, actually it doesn't matter. Minus EV over KT. So if you focus on these equations for the question where they ask you whether it was uniformly doped or not, you can tell from here that just because this difference stays the same, this numbers has to, you know, remain constant. So there is no change in the doping as you move across. That's like the math behind it, other than like the intuition of like, oh, the difference between them is the same. And in terms of the p-type, it follows the same thing. As you can see, this difference will make this number a bit bigger versus this one, just because this distance is bigger. It's an exponential decay, so it'll decay faster. Okay. Then the other question is if it's not degenerate or if it's degenerate. Do you guys know what being degenerate means? Not in like the dictionary, but like a semiconductor that is degenerate. You guys know what that means? Fermi level is above or below. Correct. Yeah. So if you dope it way too much, the Fermi would go here, or it will go here. So is it degenerate? Correct. It's not degenerate. So I don't think you guys should worry too much about this, but just for the sake of saying it, do you guys know what's low level injection versus high level injection? I recently got called on that in my 121B class, and I was on my phone, unfortunately, and I could not answer. So right now it's very engraved in my brain that a low level injection is when the number of carriers generated do not affect the majority carriers. this could be like you shine light into it and you're generating electron hole pairs, but it's not enough to be a change in the majority carriers, but it's enough to change the minority carriers. So minority carriers do increase, but majority carriers is so big that that small change you're making is basically irrelevant. So you can just say that, oh, low level injection, just minority carriers increase versus a high level injection. I guess that's kind of intuitive, you know, number of carriers generated, effect, reasonability, effect, okay, sorry, effect majority carriers. So if you increment, it's so much that the majority carriers will increase. It's not like to a million add one, still a million, but to a million add half a million, you know, it's significant. So that's kind of like, that's how I like to see it. Low level injection, it's you're adding ones, twos, threes, versus high level injection, you're adding like big quantities. So it makes a change. But I don't think that's too important. Like I didn't really learn too much about on EE2. Is it intrinsic or extrinsic? This should be like kind of, there is a previous part that you already had to answer something that gives away. Perfect, extrinsic, yeah. Because you know, you said it's a p-type, so it has to be extrinsic, else none of this matters. So that's correct. And I feel those, at least for me, those type of problems are really hard. Having to look at a graph and come up with stuff. So I have two more problems. One of them is on capacitance. I don't know, it's a little long, not too long, I guess, if we skip some of the math. Or I also have one that I feel is pretty cool problem. It's short and it's cool. So I don't know, you guys want to take a break? Maybe just like a 5-minute. So you guys have been at it for. No. Okay, we'll go over the cool problem for sure. Whoa. Okay. It's not there for some reason. Okay, so I'll draw the bar because I don't know why when I imported it didn't come through. So this is 2016. Okay, so the problem tells you to consider two p-type silicon bars are uniformly doped. It says that bar 1 is doped by 10 to the 16 and bar 2 is doped 10 to the 19. These two bars are brought together in contact with each other, as shown in the figure. Explain what happens when you bring these two bars together. We'll draw a whole concentration profile of this junction, and then ask you if the whole concentration becomes uniform across the bar. So I'd like to start these problems. Perhaps it's a slow way to do it, but I might even try to color code it so it's not confusing. So you have bar 1 and you have bar 2. So this is the conduction band. Okay. Can anyone tell me for the first bar, will the Fermi level be below or above this? Below, correct. So I'm gonna pick arbitrary number and positions. This would be EF. And since we know that the second bar has a higher doping concentration, this should be closer to the valence band. Well, this should be F2. And this should be F1. Okay, so this is at least my way to do these things. Might be cheating because I have an iPad, so if you don't, that might be a little bit difficult, but this is the way I do it. So you do them separated. We know that at least so far, those two are correct. One thing that is true always is that the Fermi level is constant through the device when it's in equilibrium. So that will hold true for this problem too. Like that's how p-n junctions are created, you know, that like difference levels, the Fermi level has to remain constant. So knowing that much, we can go ahead and say, well, if the Fermi level has to stay constant, you can take bar number 1. We don't need that anymore. You can take bar number 2. And then you can focus on just align the Fermi levels, because you know that's what has to remain constant through both of them. I'll use a third color. We'll use purple. Right, the Fermi level has to remain constant, which means that the bending of the bands should be, maybe should have made it more dramatic so it's easier to see. So that would be kind of like, can you guys tell if this is bending? Like, I don't know. I feel in my notes I made it a little bit more dramatic. Okay, thank you. Good. Yeah, so the Fermi stays constant and the conduction in Bell is bend. So that's as much as they ask you in regards of that. But I feel it's important to know physically what's really happening, like why that happens. You know, in a p-n junction, you know it happens for a reason. It's a n and a p, they cross over each other. But like these are both p's. So I feel like it's a type of problem that you know how to do because you know how to do p-n junctions, but it's a p-n-p, so it's a little, you know, you have to be cautious about what you, I know it feels different. So I'll just spend, I think it's worth to spend some time on what happens physically when you connect bar 1 and bar 2. So physically, when you put them together, the holes of bar 2 will recombine with the electrons of bar 1, just because that's how the concentrations are. So you're gonna have this little free electrons gonna jump here, and they're gonna leave behind here so where they will recombine. So they'll create some immobile charges, negative charges on B2 and positive charges on B1. This will generate an electric field, and that electric field will oppose the diffusion until they will reach an equilibrium. So that's physically what's happening. It's the same process as a p-n junction, except now it's like with only holes, but you're gonna focus on the holes that are on the most doped side. That's a small side note. They also ask you to, will the whole carrier concentration become uniform across the composite bar? So one good thing to see these problems, that particular type of problem is, I like to think when I'm super far away from the junction, what happens? So if I'm super far away from the junction, am I going to see any effect in regards to the concentration of holes? I should not, right? So this should still be 10 to the 19 centimeters, negative centimeters cubed. And this should still be 10 to the 16 centimeters cubed. So those two things have to stay true. So what will happen is we'll have some sort of bending at the junction. So the whole concentration will not be constant across. Like it'll have this bending. You won't bring this entirely down. You won't bring this entirely up. When you're far away from the junction, they'll remain the way they were before you combine them. And I don't know, I thought it was a cool problem. That's the one I thought it was cool. We have to 7:30, right, Cody?
Yes, correct. You have until 7:30.
That is interesting. I didn't know. Okay. I can go over that junction capacitance problem I was telling you guys about. Maybe just the highlights of it. I cannot have to go into much detail if you guys want. That was like the last problem I had prepared. I don't know. I couldn't hear what you said before, Cody. So I'm not sure. Should I go?
Oh yeah, go for it. I was just saying that like if you have extra time after this,
Anything.
like we can just like if you have any specific questions, we can answer them.
Or should I go over it or no? I'm sorry. My computer is just being super weird.
I mean, if you're having technical difficulties,
Yeah, I'm really sorry.
it's fine. I also have like a question on, I have a question on a qualitative question on phonons that I think might be interesting.
Okay, that's yeah. If you that's what I'm saying. I don't want to like finish this if you have
Sure.
something else to go over. Okay.
Sure.
I'll stop sharing.
There we go. So in class you might have learned something where it's like if you have a direct band gap, like there's no scattering, right? But if you have an indirect band gap, like in silicon, then what happens is there's some scattering, right? So let's see. Can't draw on here, but basically a direct band gap is like there's a straight line up from the conduction band to the valence band, while indirect means that there's like the conduction band electrons like right here, and then the valence band is like right here. So like it's like at a diagonal. And so how does phonon scattering scale with temperature? Yeah, that's correct. So lattice scattering, as Alexander said, lattice scattering is the scattering from vibrations of the lattice phonons, and ionized impurity is from the doping ions. Ionized impurity scattering increases with temperature, while lattice scattering also increases temperature. One sec, let me check. So yeah, phonon scattering due to thermal motion of particles with related to temperature. Phonon scattering is temp decreases, less vibrations, less effect from phonons. And ionized impurity is, yeah. Wait. Phonon scattering is proportional to T to the -3/½ power. And then ionized impurity is proportional to T to the 3/½ power. So that's like the temperature dependence. And then, yeah. Okay. Quasi-Fermi energy. Oh, also, I think it's good to know the like what an abrupt p-n junction might look like. So an abrupt p-n junction is just like this, where you have like on one side it's like you have the holes, on the other side it's like the electrons, and it models the p-n junction pretty well. And what else? But in an actual device, you don't get like abrupt changes. You have something that looks more like this. And yeah. That's all I have. Yeah, okay.